Hello, wonderful students. It's good to, I guess, see you. As you can imagine, video lessons are just not going to be my thing either. So, anyway, as we jump back into chemistry here, because I mean, I could probably safely assume you've all been doing this every day, but just in case you haven't, I thought I would start us off by jumping back into the Lego analogy relating to stoichiometry, just to kind of refresh you on that. And then what I'll try and do here is make an analogy from Legos and then jump right into seeing it in actual chemistry. So before we jump into this, a couple things to remember. One, atoms react based on the number of valence electrons, not the size of their or the mass. So it is important to remember that when you look at a periodic table here, right, lithium is physically going to be a smaller atom than sodium. Lithium has fewer protons, neutrons, has fewer electrons, so it's physically a smaller atom. However, it's going to take one lithium to react with one fluorine, just as it would take one sodium to react with one fluorine. But the masses are going to be very different. So just keep that in mind. Two, since the number of atoms matters, we needed a consistency to be able to measure them, because I can't just say 5 grams lithium, 5 grams sodium, because that's very different. There's going to be a lot more lithiums in 5 grams than there would sodiums, just like there would be a lot more tennis balls in 5 pounds than there would be in bowling balls, because lithium's much smaller. So scientists needed a consistency for that, and unfortunately we can't get down and measure atoms. So they came up with this consistency that 1 mole was going to be 6.02 times 10 to the 23rd of really anything but atoms, which 1 mole is equal to that many atoms, which is also equal to your mass on the periodic table. So if we were to jump into an example here, let's just look at sodium, because we'll be using that in this problem. We can say that 1 mole of sodium is equal to 6.02 times 10 to the 23rd atoms of sodium, which is literally the same thing as 22.99 grams of sodium. So again, just keep in mind that scientists use this because if we were able to get down and literally count atoms, we would just do that. We probably wouldn't use mass. Unfortunately, we can't, so we have to use this conversion of mass. So let's jump back into our Lego analogy here. I could say that 1 brick is equal to, and maybe I'll just make up, I think the number I used in class was 10,000 atoms. Let's just, again, it's just a simpler analogy. It's an easier number to work with than 6.02. Is every Lego brick 10,000 atoms? No, it's far more. This is just an analogy. And I think, I don't know, I don't remember. Let's just pretend that 1 Lego brick weighed, no, what is this? Sodium. So sodium's actually the smallest of all of these. Let's pretend it was 0.72 grams for that Lego brick. Okay, so maybe I have that number on here, and maybe if I draw a fake periodic table down here for Legos, I could say that, my Na brick is 0.72 grams coming from the periodic table. Maybe I make up a different number. Magnesium, you can see, is heavier, not too much heavier. But let's pretend my magnesium Lego brick is, I don't know, 0.91 grams. And then phosphorus, if we look on our periodic table, is going to be a little bit heavier. So maybe we make up a number and say that phosphorus now is 1.41 grams as a Lego brick. Obviously, those masses are a little bit different, but we're going back to our analogy. So to kind of look at a problem like this, let's say I wanted to convert from, and I'm just going to give you a full problem. Maybe we have, and I'm going to pause for a second here to write this out. So we have this problem here. If we have 21.84 grams of magnesium, how much magnesium phosphide could be produced? And we'll actually use this equation that's up top here. So what I'm going to do is, let's actually just use those same numbers regardless if it's our Lego values here or if it's our periodic table one. It actually doesn't really matter. But I know some of us like the Lego analogy. The numbers are a little bit easier, so let's just start off with that. So if we do this, what I'm going to do for the Lego one is let's just pretend I told you we have 21.84 grams of magnesium, and you also know that each Lego brick is 0.91 grams. A lot of you would just probably be able to reason out, and I asked you how many Lego bricks do I have? That's the same as how many moles of magnesium do I have? A lot of you would probably be able to reason it out. Okay, so you have 21.84 grams of, I guess we'll say magnesium bricks. Well, each brick, I think the number we made up was 0.91 grams of magnesium, and we can just say that's per one Lego brick, right? And if we actually stopped right here and just did this math, we would find that there would be 24 magnesium Lego bricks. Right? In this case, I actually wrote the problem to give us a nice clean number. So that's how many Lego bricks there would be. Now, if we wanted to see the same thing in terms of like the chemistry mole, remember our numbers probably aren't going to be as clean, and they're also likely not going to be a whole number because we need to remember that a mole actually represents this many atoms. So while you can't really have part of a Lego brick, you can definitely have part of a chemistry mole because it just means you have fewer atoms. But this process looks the same. We're going to take our 21.84 grams of magnesium. But now looking at our periodic table here, we can see that an actual magnesium mole is 24.31. So we should expect it will be close to 1, but this number is a little bit smaller, so it'll be less than 1 mole. But we would put our 24.31 grams of magnesium on bottom. And now on top, instead of writing bricks, we're going to write 1 mole of magnesium. And if you plug this in, you will find that you would actually get 0.898 moles of magnesium. And that makes sense. Since we had 21.84, periodic table tells us that there's 24.31 grams for every 1 mole. The answer makes sense. For those of you that are feeling confident with this, I'm actually going to go ahead and just put the number up here. So you can actually try and pause the video right now, work ahead. If you get it correct, great. You probably don't need to carry on. So the answer for the top one here, if you go through and solve for this, and we want to follow our sig figs, so we started with 4 sig figs, so our answer should have 4 sig figs. So our final answer here, you should get 44.40 grams of magnesium phosphide. Nope, I got that hidden there a little bit. And I'm probably going to rehide it. And then if we come down to the last one, you should get an answer of 40.38 grams of magnesium phosphide. So if you pause the video and try these out, there you go. Those are answers. If you got them correct, great. You probably don't need to listen to the rest of this. If you didn't get those or you're still confused, let's jump back into the analogy. So looking at over here at our magnesium example, please remember that this number will always come, I think I always tell students, PEP. So this would come from periodic table. The next bit of information will always come from your equation. So including from up here. Now is where I always had a student and I, Danny, a lot of times, would trade pieces. So what will happen is it's basically asking how many magnesium can I trade and for how many magnesium phosphide will he give me? Well, in this case, if we look at our ratio, I have to give Danny 3 magnesiums. And maybe I'll write, bricks of Legos or whatever, for every 1 brick of magnesium phosphide that he would give me. Fantastic. So if and a lot of us could actually reason that, well, if I only have 24 bricks here, and I have to give him 3 for 1, how many am I going to end up with? Well, he would be willing to give me 8 bricks of magnesium phosphide. Same exact process happens down here. It's going to take 3 moles of magnesium within that reaction to produce 1 mole of magnesium phosphide. And we could go through and solve for this, and if we do that, we would find, and we would expect the number to go down, we would find 0.299 moles of magnesium. And you know, there's problems where we might ask you something like this. I might ask you just go from grams of one substance to moles of another. If that's the case, you just stop your railroad tracks here. I'm just showing you the longest problem I would give you of like grams to grams. I guess I could add in atoms, but for the most part, this is the longest problem I would ask you, is to go from grams of one substance to grams of another. But I could ask you just go grams to moles of the same substance, you would stop there. So you just stop where whatever the question asks you. So now it would be like if Danny gave me these 8 bricks of magnesium phosphide, and I was like, well, how much do they weigh? Because in chemistry, I can't get down and count how many he gave me. I'm going to have to put them onto a scale. And so what should my expected outcome be? Well, that's where all we have to do is picture if he literally took 3 bricks of magnesium and 2 bricks of phosphorus and added them together. How do we find out how much that 1 brick weighs? Well, we would know that 1 brick of magnesium phosphide would weigh, and what we're going to do is we would just take 3 of these. So we would take, I'm trying to find where I want to write this. I'll just kind of write it down here. 3 times our weight of that magnesium, 0.91 grams, plus we would have the weight of 2 bricks of phosphorus, which we made up a mass of 1.41 grams, and we would find that combined those have a weight of 5.55 grams. And that's actually per 1 Lego brick. Even though technically, right, that Lego brick is now a molecule, it's a combined thing, but we're going to count it as one thing. So we would write, okay, well, for every 1 brick of magnesium phosphide, 5.55 grams Mg3P2. And so now on the scale, we would actually be able to find this answer. We would find that Daniel would have had to measure out 44.40 grams of magnesium phosphide. And so that's what our trade would look like. If we came down and did, continue to this same problem on in terms of chemistry, again, I wrote on here, the first conversion, your grams to moles, always comes from periodic table. This next part of PEP always comes from your equation. That's that trading phase that Danny and I go through, or whatever student and I go through. That came from our equation up here, just like trading Lego bricks. And then we're back to the information coming from the last P of our PEP acronym comes from our periodic table again. And so the way that I would do that is the exact same thing. Magnesium on a real periodic table is 24.31 grams. Well, there's 3 of them, so we're going to multiply that by 3. Plus phosphorus, if we scroll over here, is 30.97. And since there's 2 of those in there, we're going to multiply those by 2, and we would get a combined mass of 134.87 grams. Well, so for every 1 mole of magnesium phosphide, there was 134.87 grams of magnesium phosphide. So now if we plug that in, you should get that answer of 40.38 grams. So there we go. That is our Lego analogy in a recap. I hope that helps. Last thing I could say is, picture if we didn't start off with this last phase right here, right? If I didn't ask you grams and maybe instead of this, I started you at moles. Well, you would just start at this step here and then continue on. You wouldn't need to do the rest of it. So just keep in mind that, I'm giving you the full gram to gram problem. And there we go. Thank you for learning with me today.